Okay, let's look at this problem. So what I have is, again, a simple supported beam. I want to find the internal forces at C, but I have this triangularly distributed load. So I'm going to cut the structure at C. That's what the problem's asking for. And let's look at, again, a left side or a right side and try to make a choice. Okay, in terms of reactions, it's a wash, right? Because you have to find a reaction for A. If you do the left side, you have to find a reaction at B for the right side. So no obvious advantage yet. What's the shape of the loading on the left-hand side? It's a triangle. What's the shape of the loading on the right-hand side? It's a trapezoid. Ouch. I don't remember the centroid of a trapezoid off the top of my head. Do you? I know the area of a trapezoid. That's easy, but I don't know the centroid. So what most people do is they cut it up into a rectangle and a triangle. And you would have to deal with two concentrated equivalent forces. Not undoable, but I think more challenging than a single force on the left-hand side. Does everybody see that? Mm-hmm. So I think the best strategy would be to go to the triangular edge or loading section, and we'll just do the left-hand side. So if I want to do the left-hand side, I just need to find the reaction at A. Now, since I fouled this diagram up with this discussion, I'm going to have to redraw it. So I'm going to draw a free body diagram and assume a reaction at AY and BY. Technically this is a pin, so I'll have a reaction force in the X direction. Now I'm going to find the concentrated equivalent force of this large triangular force. Remember, the area of a triangle is 1/2 base times height. So the base is 18, height is 3, so that would be 27, area under the curve. So I know the equivalent force has a value of 27 kips. And where's the centroid of a triangle?
12 from A.
The way I remember it is 1/3 from the big end. However you want to remember it. So 1/3 from the big end would be 6 feet on this side and 12 feet on that side. So with that done, and the fact that I want A, I'll come over here and I'll quickly sum the moments at B. Make sure I have equilibrium. Now, I'm using right-hand rule, so what kind of moment is 27 creating about B? Positive or negative? Positive. So I've got a force of 27 kips times a moment arm of 6, and then my reaction, negative moment, times a moment arm of 18. So it looks like AY is equal to 9. Nine?
Yeah.
9? That's not German. I'm at is number 9.
Yeah.
Okay. We can also quickly check, which should be pretty obvious if you look at it, that if you sum forces in the X direction and make sure it's in equilibrium, all I have is AX, so I'm done. So now I want to come down and draw my free body diagram for AC. And let's see what we've got. So I'll try to draw this a little bit bigger. So I have my AY reaction, which is 9 kips. It has a length of 6 feet. And then I've got this triangular load. I'll come back. Well, let's talk about that now. What's the intensity of the load there? If it's 3 kips per feet all the way out here at the end, it behaves linearly. So what would be the height of the load here?
9. 1 kip per foot.
Yeah, 1 kip per foot. It's similar triangles. So this height is to 6 as 3 is to 18. You guys see that? So this should be 1 kip per foot. So that means the concentrated equivalent force would be base, 1/2 base times height, which is 3. And the distance from the big end is 1/3 the distance, or 2 feet. Then all I have to do is remember my sign conventions. Positive shear, positive axial force, positive bending moment. And I'm 60% done.
How did you know it was 1 cup per foot?
If you look at the load, I know it's 3 kips per foot on the end at a distance of 18 feet. And it's linear. So if I come over here, and I don't know what the height is there, but I know this is 6 feet, right? Then similar triangle says the unknown value is to 6 as 3 is to 18. And what's 3 divided by 18? That's 1, 6. So what should the question mark be? 1. So all I'll do is finish this, just apply my mechanics. So I'm going to sum moments about the cut. Make sure it's in equilibrium. Again, using right-hand rule. So this bending moment is a positive moment. The moment caused by the concentrated equivalent force, 3 kips, creates positive moments about the cut. 3 kips, and its moment arm is 2 feet. The reaction force creates negative moment, and it has a moment arm of 6. So it looks like the moment in this structure is positive 54 minus 6 is 48. Does that sound right? And it's positive. Right, Mr. Abney? Positive moment.
Yes, sir.
Do you like that?
I do like that.
Because how's this beam going to bend?
Like a smiley face.
Like a smiley face. Excellent. One more thing to do?
That would be like a smurf.
What's that?
That would be like a smurf.
A smurf?
A smurf.
A smirk. I was going to say,
That would be
a smurf would be okay. Most smurfs are happy and smiling all the time, right? So it could be a smurf too. I think. I don't remember the Smurfs. You guys remember the Smurfs?
If they were green, they would die. If they were blue. So
well, those movies that came out recently were a little bizarre. They weren't quite Smurfy for me. It's not the way I remember the Smurfs. They're a little too modern, I think. That's not important to this problem, I don't think. So, summing forces in the y direction, assuming up is positive, I have a shear force V down. I have my 3 kip force down, and I have my 9 kip reaction up. So shear is equal to 6. And we're done. Any questions about that? All right.